So moving on, what is torque ripple? Torque ripple is really the dynamic part of torque on top of a steady state condition. So I think a good way to demonstrate that is with this top right graph, where I have just a load step applied to an electric motor. And we see that torque has this big dynamic swing where we have this frequency and amplitude and settling time onto a given point. And I think a lot of people are used to looking at torque as a filtered quantity. So you might see when you apply a load step that you get this slow application of load. That's a very filtered measurement, and that's not really real. Torque actually has a lot of dynamics to it. Now we're here to talk about torque ripple, not necessarily dynamic torque. But if we look out at the end of my top right graph, we can see these little bumps. And some people might think those are noise, but if we zoom in on that segment, once the torque has reached a steady state, and we look at the bottom graph, we can see that this torque is oscillating around an average. And in the red, I have my instantaneous torque, and in the black, I have my average torque. And we can see that this ripple has both periodicity and amplitude. And these peaks and valleys are actually what consists of torque ripple. Now we're going to talk all about what causes torque ripple and how it comes, but it's really worth noting that torque ripple is really just an AC component on top of a DC torque. So torque in an electric machine takes form as almost a DC value, but the ripple is this AC quantity on top of it, and it's cyclic in nature. So where does torque ripple come from? Where does that AC component come from? Well, we kind of have to understand how an electric machine works first, and understand that most electric machines are being powered by some sort of AC electricity, so AC voltage and current. And in a lot of traction applications, this is three-phase AC. It could be six-phase, it could be single-phase. These just really come down to what the ripple amplitude and frequency is. But in our three-phase machine, torque is actually going to follow the max amplitude of current that's being seen at a given time. So if we take our three-phase measurements and we just follow that envelope of what the max is, that's going to give us our torque ripple, or at least the fundamental component of it. And if we look at the graph on the bottom, we see that the green, torque in green, I guess my label got cut off, I apologize, but green is our torque, and it's following the envelope of that maximum current at any given time. So we get this kind of inherently AC nature to torque, and the average is going to be somewhere right around the middle of it. But the torque is following the peaks of the current. The frequency of the torque ripple is going to be proportionate to the RPM. So the faster this fundamental frequency is going, the faster our torque ripple is going to come. And the more phases there are, the more ripples there are going to be per mechanical rotation. So if we have a six-phase machine, we're going to have 2 times more ripples than we would have with a three-phase machine. And there's going to be some amplitude adjustment there too. The six-phase machine might have half the amplitude but twice the frequency, and vice versa. So things to be considered, but a lot of the ripple component does come from the AC excitation. Now the ripple can also come from the actual construction of the machine. A lot of us are going to be looking at permanent magnet motors, the permanent magnet motor really being the most popular for mobile applications or power dense applications where we really care about efficiency and power density. So in these machines, there's a magnet that has a DC magnetic flux, so it's always on. You can't turn this magnet off. That's going to be spinning around the rotor. Now, if you've ever walked up to a permanent magnet machine and tried to spin the shaft when it wasn't connected to anything, you'll notice that there are these bumps you overcome. And when you're overcoming these bumps, you're actually pushing the magnet through the stator slots, because the stator and the stator's construction is a big chunk of iron, and the magnets want to attract to that iron. So you have to overcome this. And then once the machine's spinning, once it's under excitation, it's still a magnet. The stator is still chunks of iron, and you're going to create ripple based on that interaction between the magnet and the iron. So these are probably the most popular one, especially for torque ripple, because you cannot turn the magnets off. A reluctance-based machine, this is really just a chunk of iron in the middle with pulses of current going through the stator that iron wants to attract to. This is just going to create really hard torque pulses. It's actually going to expand and contract the machine based on where the excitation is coming from. So these hard torque pulses are going to give it this inherently cyclic nature. This is actually probably going to be closer to what you would experience in an engine with pistons firing as far as the torque signature, depending on the excitation. But really interesting case there, and you're going to have a lot of noise and vibration issues with these reluctance machines. And then lastly, the induction motor. The induction motor has been kind of the workhorse of industry for the last 150 years. And the way it works is that if you walk up to an induction motor and you try to spin that shaft, it's going to spin freely if it's not under excitation. But once you put that three-phase power onto the stator, you're inducing magnets in the rotor. And the iron bars in the rotor are going to become little magnets. Now, they don't have the same amplitude and they don't have the same intensity as the permanent magnets. It's still going to be a magnet on the rotor interacting with iron on the stator, and you're going to have an inherent ripple because of that. So the ripple content does largely come down to the construction of the machine itself and how many slots there are, how many windings there are, what the magnet on the rotor looks like. So now, as an example, if we look at torque ripple itself, in the image I have here, we have a three-phase current excitation in the reds, and then in the blue we have our torque ripple. And we can see that this torque ripple has a offset, it looks like it's about a 20 Newton meter average torque, but there's this cyclic ripple on top of it. And we can see that per one electrical cycle, we have 36 ripples. And these ripples are being caused by the permanent magnet. This happened to be a permanent magnet machine. The excitation. So the fact that there's three phases is going to have something to do with it. The number of slots on the stator, the number of magnets in the rotor, and then if there was any suppression techniques or not are all going to affect this ripple. But in this example here, we have about a plus or minus 1 Newton meter ripple on top of a 20 Newton meter torque. I mean, that's a fair amount. That's 5% of ripple. So that might be something that needs to get mitigated. But I really like this example because it shows that the frequency of the ripple is proportionate to the construction. And then if we increase the AC excitation, that frequency is also going to go up. So construction has to do with how many ripples per electrical cycle, and then the frequency has to do with rotational speed. And amplitude is going to be really all over based on the operating conditions. That's a hard one to give you a hard, fast rule for.